All right, so last one, 612. We have points A, B, and C. I used the chalk I broke. Did they give a thing in the problem statement? Okay, yeah. I just shoot it this way. I like it this way. Some height. Okay. The points A, B, and C are the vertices of an equilateral triangle, 10 meters on a side, in an air medium. A bare point isotropic source of 1 MeV photons, strength 10 to the 13 per second, is to be moved from point A to B at a uniform speed of 0.5 meters per second. Estimate the ambient dose equivalent accrued by an unshielded observer at point C. Neglect exponential attenuation and buildup in the air. So neglect exponential attenuation and buildup in air. So we are in a vacuum. No, the problem says air. We're not considering air, because it says not to. Even when it says air, we don't use air. So this is equilateral. So this is 10 meters from on each side. So this distance is 5. From before, we're going to have our total fluence is going to be equal to 2 uncollided fluence. I'm just going to call it fluence 1, because I'm going to break this down and just do half the triangle because it's easier. So the easiest way about doing this problem is by finding how many photons are emitted per distance along here. Just turn this into a line source. We've probably talked about this before in class. You're going to walk all the way along here, and you're just going to be a line source all the way through here. And the flux will change at point C as you move from point A to B or B to A, whatever. The flux will change, but at the end you're going to get some fluence independent of time. So that's what we're going to calculate. So we're calculating the dose, not the dose rate.
Wait, why isn't it, say that again, why isn't it depending on time?
We're looking for the fluence, not the flux.
Okay.
So the flux is the time derivative of the fluence.
Right.
Yeah, it's the rate of movement.
Yeah, so this is equal to, so this is going to change because you're going to get closer, and the closest point is going to be at point, whenever you're right here, and it's going to get slowly smaller and smaller and smaller. This will, the flux. So we don't care about the flux right now. We just want to know how much fluence, how much dose do you get, has this observer get right here. So we need to find how long we're going to go right here. So we're traveling at a velocity of 0.5 meters per second, very slow. And so distance equals velocity times time. Time is equal to distance divided by velocity. It's equal to 10. Sorry, I'm using this. 5 meters divided by 0.5. I get 10 seconds, I believe, 10 seconds.
Yeah, 10 seconds for 1/2.
For 1/2. So the total time it's going to take is going to be 20 seconds, but we're looking right here, 10 seconds. We're looking at just this down here. So the photons emitted in those 10 seconds, oh man, I did 20 seconds in my notes. So the source strength is going to equal the rate of production, gammas per second, times 10 seconds. Oh, that's easy. I'm going to have to do math for you 10 to the 14 photons per second, or photons total emitted. So, so we have to find out what these values are. If you want to find out what H is, you use trig, and you get, this is 866 centimeters, and this, no, I don't like meters. So this is going to be, 10 meters is 1,000 centimeters, and this is 500 centimeters. Makes my life easier. This angle right here is 30. So it's a similar problem as before. We have our flux is equal to flux 1 is equal to from 0 to 500 centimeters. This is x, right and sideways. So from 0 to 500, we're going to have geometric attenuation. SL is our line strength, dx, 4 pi r squared, where r is whatever distance you are away from point C. So r is a function of x. R squared is equal to h squared plus x squared. So phi1 is equal to 0 to 500. SL dx over 4 pi h squared plus x squared. Once again, it's easier to turn it into trig. Saying that x is equal to tangent theta times h, and dx is equal to h secant squared theta d theta. From 0 to 30, this is now in degrees. SL h secant squared theta d theta over 4 pi h squared plus h squared tangent squared theta. Pull the h squared out, and you get trig identity. The secant squared goes away, and this goes away. So we're left with a not so bad integral, 0 to 30, SL d theta, h is also in here, h 4 pi, or h squared 4 pi. So one of the h's cancels, and like I said, it's not too mean integral, it's just, it's trivial, because it's all constants. Okay, so this is going to give you some value. I'm not going to tell you what the value is because I don't know. But I can tell you that whenever you multiply that value by 2, you get 1.92 times 10 to the 7 centimeter, or per centimeter squared. So lots of photons in there.
Is that 10 to the 7?
That's 10 to the 7. And the way I found my line source, this is a line source. This is 10 to the 4. 10 to the 4 photons. It's going to be spread over 5 meters, or 500 centimeters. So you divide by 500 to find the per centimeter.
Would it be acceptable just to integrate at the beginning with respect to x instead of going through the trait substitution?
That's fine.
Where'd the 30 come from on the integral?
That is the angle. This
Oh,
angle.
right.
Cosine 30, or sine 30 is 1/2.
Sorry, does it go from 0 to